What's good, bruz? Today, I don't like it. I don't know. It feels funny. It's not inappropriate, right?
No.
It's just dumb. Okay, good. All right. Not dumb. That's not the right word. Looking at it, I saw a few different options. Nick, I don't think, just to call you out, not in a bad way, I hope. I don't think you quite got the question, but that's all right. I'm not super worried about it. Looking at this, they clearly have to interact somehow, right? We're not flying off into space, and it's gravity that causes that centripetal force that keeps us in orbit. We've talked about that at length. Now, the sun's way bigger. So the natural assumption, and I wish I had written this differently. I'm going to draw it right from the center of the planet. The natural assumption, or the sun, the natural assumption, what I saw a lot of you have, don't draw this until like we're done talking about it. A lot of people drew this, and I did that exactly backward. A lot of people drew this, said, hey, the sun pulls really hard on the Earth, and maybe the Earth pulls a little bit on the sun. That seems reasonable, but it's not true. Okay, this is not how gravity works, and we'll go into the more specifics of gravity throughout today and next lesson, but in reality, what winds up happening is they're the exact same. Doesn't matter that the sun is like way bigger, way heavier. Not at all. They have equal but opposite attraction to one another. Now, if you were to look at this, we use this all over the place. I don't personally, I guess, but maybe some of you will if you ever become astronomers or cosmologists. As you're looking at this, if we look at the stars and we want to know if there's planets around another star, which there are, there's lots of them, it's really hard to look really far away and see a planet, right? They don't emit light. It's super challenging to see. We just can't see it reasonably. What we can do, however, is recognize that because this happens and they're going around each other and there's a bunch of other stuff, it's constantly being pulled back and forth. We don't feel it, but when we orbit, it really does this. So if we want to know if a star has planets around it, astronomers, look for the wobbling of a star, because a wobble from a star leads to the conclusion that there's something making it wobble, and pretty naturally it's going to be a planet, or a lot of planets. So as we get through here, let's see, Copernicus died in, I don't remember the year, I don't think you guys wrote it down. If you did, whatever, that's fine. Copernicus did all his big stuff. 1543, he published his book and then immediately died afterward. Bra, or Tycho, if you want to refer to him as first name, which seems odd. He was psyched about this, saw an eclipse, thought, wow, that's neat. Started studying underneath Kepler in 1600. Kepler pieces out about a year later, and Kepler develops his laws after the death of Tycho. Okay, don't know exactly when Kepler died. I'm not sure, I don't recall. Regardless, Isaac Newton was born about 60 years later, after Kepler had started working with Bra. So, as we go through here, we are continuing on. We're still in Chapter 7, Section 1. So this is just the second half. All the first stuff was observations and Kepler's law. Moving forward, we are going to hang out with Isaac. So, big one today, and we're going to define it here. And I'm going to leave some blank space because we're going to make a few comments, but I don't want to write it twice. Our main topic today is Isaac Newton's law of universal gravitation. I do not have a shorthand for this, but there's a very telltale sign that this is what we're using. NLUG sounds okay. So Newton begins his work on gravity and physics and all this at a really big level in about 1666. So this is when he first published his big ideas. Him and another guy by the name of Gottfried Leibniz developed the same branch of mathematics at the same time. It's called calculus, and they used it for physics reasons. Now, fun fact about it, you can actually look at Newton's stuff, and if anybody takes calculus next year, I'm not sure, but I think I'm going to be teaching it. If you take calc next year, one of the things we can look at is the calculus that Newton developed that led to everything else is very different looking. Like, I don't think Newton could do the calc problems that we did or that we do nowadays, because there's more development from his ideas moving forward. But it's pretty cool that he was able to do this. Now, I'm going to leave blank space because it's just a formula. So I have, just so you know, on mine, here's where I have the law of universal. I'll show you how big it is so you know how much space to leave. I don't know how big you write. Okay, I don't want to spoil it, but this is Newton's law. We're going to look at it here in just a second. This is the law of universal gravitation. So it's really just one line, but we just have to say what the variables are. So on mine, as I'm looking at the board, oh, I just about ripped a button off of there. I'm going to leave about that. That's will fit all of Newton's law. Now, before we actually write this down, I just want to preface it. We're just doing this so we don't have to double write stuff. Right off the bat, Newton recognized, and I don't think the apple thing is really true, just so you guys know, but he did recognize that there was a force that we couldn't see, but we were always experiencing, and it's known as the gravitational force. Gravitational force. Now, for this, we are going to get some new language out of this, and we'll all be able to make sense of it. But right off the bat, gravitational force. Is it attractive or repulsive or both? It only attracts. We've never seen gravity repel. Now, furthermore, we don't have to write this part down, but it's one of 4 fundamental forces of our universe. There are only 4 main rules that have to be known and thought about and worked out to really talk about anything that ever happens in the universe. Gravity is one of them. It is the least understood of the 4. Gravity's crazy. It's strange. There's no good full theory of it, although we have pretty good ideas. Okay, gravity's one. Anybody know another one? Are you interested in knowing them, or you just want me to keep talking about this? So check it out. Gravity's interesting. It's really weak. It's like crazy weak. Electromagnetism is another fundamental force of the universe. Magnets and electricity are the same thing. They're just opposite sides of the same coin, which is a weird idea. Have you guys ever done much stuff? I think I already asked this, right? You ever seen electricity and magnetism stuff? So we'll do the same thing if we wind up studying it. I'll show you a neat little demonstration with it that I'm going to show my later. Is it worth showing? Okay. I showed gravitational force. It only attracts. And I'll deal those magnets back here in just a second, because I think if they're not too distracting, I'll let you play with them for the time. But cool. Okay, gravitational force. We're just going to say that this, by definition, do you have to be touching something to feel its gravity? So it's not a contact force. It's a field force. They generate gravitational fields, which we'll talk about a bit more later. We're just going to define it. It is the attractive field force. The attractive field, which just means non-contact, force between, and this is pretty cool that it works, I'm going to say any. And I'm going to underline it because that's important. Any 2 objects in the universe. Okay. Now, for this, everything is always attracted to each other gravitationally. Every single one of you right now is applying a gravitational force to me, and I'm applying the same force back at you. Every single one of us. But why don't you guys all just get pulled into here? Why isn't my gravity strong enough to make all of you like blast up here all of a sudden? I'm not big enough. Thanks for that compliment. Okay, looking at this, we have bigger stuff around us that gravity's stronger that overcomes this. Now there's some other things going on here, but it doesn't matter which 2 objects you're talking about. I'm here on Earth. I assume that there's a supermassive black hole billions of light years away. I'm pulling on it right now. I am. It's pulling on me. It is. But it's not strong enough to be noticeable because, we're on the planet. So, looking at this, any 2 the same. As we're looking at this, couple follow-up comments. Equal but opposite. So I'm pulling on the sun right now, and it's pulling on me with the exact same strength all the time. It's never different. Now, there are other objects in the universe, because I think there's more than 2 things, so everything's constantly pulling on everything, and it can be really complex to see who wins, right? But obviously the Earth wins in our classroom. Now, Newton's law, what he was able to work out is awesome. He found out that when you deal with this, there's 3 big things, that matter. You need 2 objects and a distance between them. That's like the bulk of it. So here we go. Newton discovered that between any 2 objects, the force of gravity always is exactly equal to the following. And it's an ugly fraction. And there's two ways you can write it. I'll present both of them. I'm going to leave a blank space first, and I'll just write my fraction bar. The first one is that it depends on the masses. So if we have two objects, I'm just going to say that they're each mass m1 and m2. We're going to multiply these. And I'll move that up so it's really clear. Force of gravity is something, blank here still, times the mass of the first object times the mass of the second. And we're going to divide it by the square of the distance between them. Now, if we think about it as a circular region, we'll just call this the radius. Okay. With this, what we are seeing right now is two different types of variation if you think back in pre-calc. It's been a while, so I get it. Gravity varies directly with the masses. So these, if you double the mass, what do you think happens with the force of gravity? It doubles. If you triple the mass, it triples. Okay, that's direct variation with the mass. Alternatively, it varies inversely, because it's in the denominator, with the square of the radius, which this one's a little bit harder. If I have two objects that have some gravitational force, and I move them twice as far apart, how did that change the force? Not quite. More or less, depending on how do I want to word this. If this was 1, this would just be m1 times m2 over 1, right? What if it was 2? Would it be over 2? It'd be over 4, right? If you double the distance, 2 squared is 4, you'd take a fourth of the power. If you triple the distance between these two objects, how does that impact the force of gravity? It's 1/9 as strong now. That's this inverse square law is what that's known as. Now, there's a big elephant just waiting here to be talked about. Turns out it's not exactly this perfect, because when you do variation stuff, and when we did variation stuff, there was always that constant of variation that we used the letter K when we did it in pre-calc. Turns out Newton discovered that there was a constant of variation here, and it is G. Capital G, very specifically capital G. All right, so for this, I will not ask you a question about this part. I'm going to label these, and we're going to make one more comment, and we'll start playing around with this. So, in this, we just need to make sure we know what stuff is. M1 and M2 represent what? Mass of objects. Okay. R equals the what? I'm cool with calling it the radius, but with two objects in mind, that radius is just the distance between them. Yep, and I'm cool with that. Like, you're absolutely right, radius, but I'm just going to say distance, and we have to work in our nice physical world, so we'll just say distance between centers. Okay, the last one, we have this G, right? The G is just a number. For now, all I'm going to say is G is gravitational constant. It is the same everywhere in the universe. These three things. Now, those I expect you to know. What I don't necessarily need you to be able to do, like for a test or whatever, this is known. Anytime you see this relationship, it's called the inverse square law. Anytime that you double the distance and it makes it 1 over the double or 2 squared, that's an inverse square. This shows up all over the place in physics. Inverse square law. It's just a really nice relationship. Okay. Now, looking at this, there's a natural question to what G is. And I'll give us one of two options. I'll probably have to tell you, just because I don't know, like even standing here, there's air in here moving around. It might throw off our experiment. But what I would like to propose is I'm going to go find some stuff. I have most of it. I want us to see if we can't find this number G ourselves. So it was found in like 1700-ish in that time, but we could do the same experiment in here. It's really slow, so we'd have to let it set. Like, we can't watch it happen suddenly. But I'm down to help set it up if we want to try to discover this ourselves too. We'll just see how close we are with a not perfect lab, right? Let's try that next week. Cool. Might have to actually try it next Friday and let it sit over the weekend, because it takes a long time for gravity to work. That's a weird comment, but cool. All right, so we have this. What's Newton's law of universal gravitation? G, what's in the numerator? What? Look at your page. What's in the numerator? Numerator's up top, sorry. G, M1, M2. Constant in mass, right? What's in the denominator? The distance between them. Cool. And it's squared, but it's the distance between them. Now, Newton came up with this, and there's all of a sudden this awesome idea that we can do. We can now link Newton and Kepler. And their names will forever be together in this sense, because their ideas and what they were studying are so related that they tie right into one another, and it's awesome. And it's going to look scary. It's not scary. When you have questions, if you have questions, don't hesitate. So we're going to think about this. We are working under the nice assumption that we're just going to totally ignore Kepler's first law for mathematical purposes. What's Kepler's first law tell us the shape of the orbits are? Make sure you're paying attention to, or else I'll take them. Say it again. They're ellipses. Okay, they are not quite circles, but they're pretty stinking close to circles, so we're going to use circular math. Here we go. Now, when we're thinking about this, I'm going to make just a small little picture. I don't know if it'll make a huge deal. Let's say here is our sun. It's awesome. Okay, and then I don't even care what's out here. Some planet lives out here, and whether it's Earth or not is irrelevant. I'm going to say here's a planet, so whatever it is, and then we're going to talk about two things, and we can dig into how they calculated out these things, but there's only a couple things you really truly need. If you're going to use Newton's law, you need the distance here, that's r, and what else do you need? The mass. So the question, not our focus right now, is going to eventually become, well, how on earth do they discover the mass of the sun? Because we did, and we can, and we will. And simultaneously, how on earth could you find the mass of any planet? Like, we can't just put Earth on a scale. But we will weigh our planet next week. We're going to do this. Like, we'll figure out what the mass of Earth is. And I know it's in our book, but it's cooler if we can do it. Cool. So here's our nice picture. Just to make sure we can identify all these pieces, we have a star and a planet, and between them there's a distance that I'm going to label as the radius r. The only other thing that we need is, I'm just going to put these dashes. It's not going to be perfect, but check it out. It orbits in a circular fashion. Cool. Two planets hanging out, chilling. Sorry, a planet chilling around a star, and we're going to get kicking here. All right. Now, we're going to tie a bunch of stuff together, so if we need a brain break throughout here, let me know, and I'll find a spot if we need it. It's going to take like 10 minutes. Right off the bat, why doesn't that planet just fling out into deep space? So gravity is the force, right, that keeps it there. But let's be a little bit more specific. Gravity produces a force that winds up impacting our net force toward the sun, right? Like directly towards the center. That force has a name if we have circular motion and there's a force pushing right towards the middle. We have a centripetal force acting here. Okay. What that means for us is, if we're working on this, I think if we want to find the centripetal force generated here, we can work it out as follows. I think that the net force, which winds up being our centripetal force, and I'm not going to write FC here, but how do you find centripetal force again? So we have the mass of, let's say a planet here in this case, times centripetal acceleration. So that's last chapter stuff, but the idea still applies. Mass times acceleration, it just happens to be centripetal. Now, going through this, as we look at things, what's centripetal acceleration again? Like, how would you find it? And I'll make some notes over here just so that it's kind of like review stuff. How do you find centripetal acceleration? V squared over r. Love it. Now, that's all fine and dandy, but gosh, to find out how fast a planet moves, it'd be really convenient if we could like track our location in space and know when we've gone a full circle, because that'd be an easy way to calculate it out, right? Now, we've already done this calculation. We can do it again if you want, but I guarantee if you dig in your notes, we will find that 4 pi r squared over t squared is what we obtain. So the orbital period winds up being the year. We've done this derivation. I'm trying to remember when we did this derivation. We did it when we looked at the period of revolution. We solved it for t before. This time, I'm just solving it for AC. Cool. All right, so all of a sudden I have this as my value for centripetal acceleration. Can I plug that in here for this centripetal acceleration? Like if they're the same thing, I can, right? Like I'm just substituting. Let's do that. Using that value for centripetal acceleration, we wind up with our net force, and I'll keep writing this, is equal to the mass of the planet, whatever that winds up being, and then instead of AC, we're just going to use this. 4 pi r squared over t squared. Now, as a quick check here, what's m sub p represent? Fern, m sub p. Love it. Felicia, r. The radius that we're dealing with, cool. Capital T, Delilah? Time, and specifically if it's capital, what specific sort of time? The orbital period. Awesome. So we have all of our stuff identified. Now, because we're moving in uniform circular motion because we're working with this nice perfect circle, there's only one force acting on this, right? And it's the force of gravity. Everybody okay with that? We're in this nice picture, assuming that we're not worrying about the gravity of other things. Only gravity's at work here. Cool, cool? Which means the net force is only gravity. And Newton hooked it up. What is the net force due to gravity according to Newton? Or what's the force of gravity? So that's only on Earth. So that's the acceleration due to gravity. The force is always mass times acceleration, and we just had Newton, big idea, show up on the board. We talked about universal gravity. What's the net force of universal gravity then? G, M1, M2. So I'm going to change M1 and M2. What are the 1 and 2s that we're dealing with in this picture? One of them's a sun, and one of them's a planet, and that's all over r squared. The only force acting on this system right now is gravity, is the only reason I'm plugging this in. And because I knew that it was centripetal force, well, we're just playing the substitution game. The right side is still just the mass of my planet times this lovely 4 pi r squared over t squared. Have I lost anybody yet? It's weird, like this is just a physics thing, all this substituting, it happens, but we're just building this up. Okay.
What's the 4 pi radius squared?
So if you look at the notes when we first talked about orbital period, and I'll show you where it is in your notes. I'm trying to remember if you were here. Whether you were here or watched the video, either way, we derived a way to write out the period of an orbit, and all that I've done is I've just rearranged this to solve instead for AC. Okay, so before we solved it for t, and I just square it, I multiply by AC, and I divide. Okay, so we get this lovely expression. Now, I think I want you guys to flex your algebra muscles, just a skosh. I'm going to give you guys a couple minutes, because I think there's value just in practicing. We could solve for like a million, not literally. We could solve for 1, 2, 3, 4, 5 things here, right? Okay, I want you to flex your algebra muscles, and I want you now, with your groups, solve this for t. Because Kepler tells us there's this relationship, right? The square of the periods is equal to the cube of the radii. We're going to link Newton's idea of universal gravitation to Kepler's idea of this ratio, or this proportional relationship. I want you guys to do a little bit of algebra. Solve this for t. I'm going to give you a couple minutes. Algebra time. All right, right off the bat, if I'm solving for t, I want t out of the denominator. So I'm going to do two things. I don't want any fractions. I'm going to multiply both sides by t squared. Simultaneously, I'm going to multiply by r squared. Cool. So when I knock this out, let's see. We're going to wind up with t squared. And then I'll just write g, mass of the sun, mass of the planet. Right? That's the left side. Equals, I still have a mass of the planet. And I get 4 pi r squared. And one more thing is going to be r squared, right?
Where's the r squared
I multiplied both sides by it. Yep.
You multiplied by t squared and r squared.
Yep, I just did 2 in the same time. Yep. Okay, everybody cool with this? All right, now what? And all of a sudden, I see a small typo that this is going to destroy everything, so I'm terribly sorry. If we look back, and I hate to do this, but I do have a typo, and I noticed it as soon as I started looking at it just now. If you solved this for a sub c, you would have to square stuff, right? And when you squared the right side, you'd get 4 pi squared what? In the numerator, right here, if I squared both sides. I would get r. Do you guys agree? About 3 minutes ago, I lied right to your faces. What did I say we got? Terribly sorry. Your assignment this weekend. Fix it. Sorry, it's going to only change one thing in the end, but I want you to continue on. If we need to finish the algebra on Monday, we will. All right. You can't minus it because it's being multiplied, but you can undo multiplication. Yep. So now I would divide everything by GMSMT. Cool. Sorry about that, guys. I'm glad I caught it before I sent you home to do it. No homework. Sorry.